can hand over to Barry now, Barry Mazur from Harvard University, who's going to talk about thoughts about Peter Swinnerton-Dyer and about the conjecture of Birch and Swinnerton-Dyer. Thank you, Barry.
Thank you, John. It's wonderful to be here. And as I look at my screen, I see so many old friends. It's just marvelous to be part of this. And thanks, John, and everyone who has organized this event. I'll start by sharing my screen and seeing whether first it works. I hope it does.
Mm-hmm.
And the title is Thoughts About Peter Swinnerton-Dyer, about Peter. It's meant to initiate discussion. I know that a lot of the things that I'll be saying are sort of old and familiar friends to many people in this audience. But, whoops, hey, what's happened here? Okay. Can everybody see this?
Mm-hmm.
But I'll start by talking about conjectures in the style of Birch and Swinnerton-Dyer. And I'll continue by giving a tiny bit of ongoing joint work with Carl Rubin, and all this in honor of Peter. I have to organize my screen a bit. Okay. Who was, as John said, and as I'm sure everyone in this audience who knew him knows very well, was warm, cheerful, inspiring, led a vibrant life, and was also important in the wider world. It's also true that every time I met him, there would be some surprise or other. For example, when he showed up at Harvard in a red Chevrolet convertible. I wonder whether, Andrew, were you there when he did that? It's radiating of all things country music, looking something like that. And I'm guessing, as I did a little bit of research, that this was when he was in a Commonwealth Fund scholarship trip to the United States. And he himself wrote, although that was in theory to travel to other universities where there was a colleague with shared interests, in practice, for most fellows, it meant going from one national park to another. And I hope he classified Harvard more in the university category than park. The other surprising, there are many surprising things actually, thing for me, and very much an education. I need some education right here in my slide. Very much an education for me is how he neatly combined two flavors of research. He used his computers, and apparently he spent 10 years in the computing lab, as John mentioned. And these computers aren't the computers like the laptop that I'm speaking to you from. They're the size of a large truck. And also, he combined that with his extremely important for our subject work with Birch and Swinnerton-Dyer conjecture. Now, Poincaré once mentioned that the intellectual divide between mathematicians were of two opposite tendencies or two different kinds of mind. I don't believe that, by the way, but anyway, that's what Poincaré said. The formal and the intuitive, but continuing in Poincaré's spirit, you can add the computational as a third category. And Peter had the gift of combining all three tendencies, not as a divide, but a synthesis. He brought vital computer experience to theoretical problems continued throughout his career. And I remember very well, but perhaps some of you have never even seen those old perforated computer punch cards that came in big stacks, and who knows what they meant, but anyway, they came in big stacks. And when Peter and I were trying to understand the specifics of various modular symbols computations, the only way in which one could do that was by computer and a trip to an IBM office at that time. You couldn't just do this on your cell phone. In any case, the two themes of this lecture around the Birch-Swinnerton-Dyer conjecture. As I said, one of the most important conjectures in our subject, and modular symbols in memory of my work with Peter on modular symbols, but I'll do a little bit of hinting at some of the ongoing work that's joint with Carl Rubin. So the Birch-Swinnerton-Dyer conjecture is, as I will remind everyone, a bridge between analysis and arithmetic, and those bridges have a very long history. They trace back to Euler, in fact. The type of bridge that the Birch-Swinnerton-Dyer conjecture has can be seen already in Dedekind's analytic class number formula, where there's the analytic side and the arithmetic side. And somehow, miraculously, there's an equality there. But nowadays, we have much more complex intertwining of basic structures. Here's a flow chart of them. There are cohomological invariants, usually Selmer modular, Selmer groups, cohomology of Galois groups with various representations. These cohomological invariants are usually interesting specifically because they connect to arithmetic invariants. The arithmetic invariants are perhaps most intensely comprehended if one sees them as coming from coming from automorphic forms. And this vertical double arrow is now a flow chart for the Langlands program. They're linked. The arithmetic and the L functions and the automorphic forms are linked together by local data and statistics related to local data. And then there are the modular symbols, which connect, in fact, to all of this. So the link. I want to think of the arithmetic and the analytic as linked by what I'll just call Hecke. On the arithmetic side, there's Frobenius eigenvalues and on the analytic side, there are correspondences, and the bridge here is in the most classical form, Eichler-Shimura. And that's what sort of links the arithmetic and the analytic. But there's a bridge. The bridge is what actually is usable to prove the strong relationship between arithmetic and analytic. And the bridge I could just call algebraic cycles, or I could be, one could be more specific, because the algebraic cycles, I'm going to do something to my screen here. Yeah, that's what I'm going to do. The algebraic cycles either come in some form or other. They could be units or Heegner points or Euler systems, and the local data is, as I called, the Hecke connection. As for the arithmetic invariants that come into the arithmetic side of the Birch-Swinnerton-Dyer conjecture, I think everyone probably in this audience knows the characters, the personalities that enter into this, that is to say, the Sheparovich-Tate group, the rank of Mordell-Weil, the actual torsion groups, and the regulator. If one wants to talk about the p-adic companion conjecture to Birch-Swinnerton-Dyer, the p-adic Birch-Swinnerton-Dyer conjecture, one would also introduce the p-adic regulator. The regulator is comes by understanding the Mordell-Weil group with its Néron-Tate norm, but the p-adic regulator comes from an analogous norm constructed from p-adic heights. For reasons of brevity, I'm not going to do anything on the p-adic side of the Birch-Swinnerton-Dyer conjecture, but we could talk about it. The classical Birch-Swinnerton-Dyer conjecture, as everyone knows, has two forms. The beginning, which tells you that the order of vanishing of the L function of E, which I call L infinity E, because there's the p-adic one I would call LP, at the central point is equal to the rank. And since you have that, you can also ask what the leading term in the Taylor series is. What's the rth derivative at s equals 1? And the answer is up to epsilon is an element. Epsilon means elementary, up to an elementary factor that depends on E. It's equal to this concoction, well known, of all the personalities in the arithmetic repertoire there, times something which is local, having to do with the local behavior of the neuron model of the elliptic curve. But that isn't the historical starting Birch-Swinnerton-Dyer conjecture, and I know that Brian is in the audience, so he might comment and tell me whether I've got it right here. The initial intuition for this conjecture goes directly from local data to Mordell-Weil rank in this rather surprising way. Local data, well, there's NP, the number of points mod P of this elliptic curve, which the null hypothesis would have it, it's pretty much 1 plus P. But then there's this error term, and I don't want to demote AP to an error term because it's, in some sense, one of the most important arithmetic ingredients in number theory. But this is what it looks like. It's 1 plus P minus AP. And the if I have it right, the historical starting Birch-Swinnerton-Dyer conjecture is this amazing conjecture, I think. The product of the NPs for p less than x normalized by division by p, because it's, as I say, the null hypothesis is it looks like 1 plus p. So we normalize it a bit to make it not go to infinity too rapidly. And then we take the product for p less than or equal to x, and the answer about what the size of that is as x grows is it grows like the rth power of log x. Okay. Or we can put it more qualitatively, since I imagine this is what Brian and Peter must have sort of thought initially. The size of the NPs, which is equivalently the size of the negative size, because there was a minus sign there in that formula, of the APs reflects in some way the size of the rank of the Mordell-Weil group of the elliptic curve. Okay. Well, you know, we are in post-Sato-Tate era, and that might seem a bit delicate because, look, Sato-Tate, and this is the histogram that describes Sato-Tate, says, among many other things, that if you consider the number of primes less than x where the NP is small, that is to say, where the AP is positive, it's pretty much the same as the number of primes less than x where the NP is big, the AP is negative. And that ratio of those numbers 10 to 1 as x goes to infinity. So if you go back to this conjecture, who knows? I mean, well, what's happening? Those NPs are they're pretty small and pretty their size doesn't seem much to reflect anything, especially given the statistics. So it's worth taking a look at the bias between the AP's negative, that is say the NP's large, or the AP's positive, that is say the NP's small, and try to imagine what Brian and Peter was faced with as they began to do their computations. The APs are negative. The NPs are the red here means that if there's a race between big NPs and small NPs, the big NPs have lost 5 times. The red entries are means that the big NPs have lost this race, and nothing much changes if you go to rank 1. What the bias for rank 0 is pretty much the same as rank 1. Well, now they lose an even number of times if we take these examples. But as the rank gets bigger and bigger, they do begin to win. And so there is in at least this bit of data, you might say there's some hint that there's a relationship between rank and size of NPs, and but it wouldn't be very convincing to me unless one did a lot more computation than considering these elliptic curves and considering the primes. We've already doing this for primes less than 10 to the 9. Okay, that's just meant to be evidence of how courageous and perspicacious the early work of Brian and Peter was to make their famous conjecture. Okay, so now I'm going to do a little bit of modulus symbols. I can't give you much detail, but there are web pages with a good deal more detail. I'm going to start with an elliptic curve and mention that there is something called the plus or minus modulus symbol. The plus or minus the modulus symbol attached to E, it's a function on rational numbers. There are quite a number of very good expositions about it, but for us, the first thing I want to say is its value will be denoted with a square brackets, and the plus or minus will occur as a superscript. And the elliptic curve is going to be fixed, so it's going to be removed from the subscript. And it's pretty much an integer, but it might have a small denominator delta. But I want to think of it, if you wish, as an integer or a near integer. Now we'll be dealing with sums of modulus symbols that are weighted by Dirichlet characters. I'll only consider primitive Dirichlet characters in this entire discussion. So let's take one of them, and you can write it the way Dirichlet or Dedekind might have written it as a function on Z, which is contained in C and can take the value 0 or an element in the group generated by e to the 2 pi I over d. I'll also only be considering real degree d cyclic field extensions, that is, say, real degree d even characters chi, which means in the plus or minus, I'll be considering only the plus modulus symbols. And we can pass through the class field theory bridge and divide and think of chi as an injective homomorphism of the Galois group of the field that it generates. Or we can have it generate a homomorphism of the integral group ring, which I'll call chi as well. And note that modulus symbols are connected by the Birch and Stevens theorem to special values, special L values, associated to primitive Dirichlet characters, cutting out those field extensions F over Q. Now that's weighted sums weighted by chi are sums of this form. I can do it this way. A goes from 1 to m, or A goes from 0 to m minus 1, doesn't much matter. And there it is. It's an element in an appropriate cyclotomic field in Q bar. And these blue things are the modulus symbols. But I can organize them, of course, according to equal values of chi. And if I do that, I can consider it as a sum of weighted elements in the Galois group, where the blue things are C alphas, the coefficients. They're also in Q, are I want to call theta coefficients. Or I can put them all together and make this concoction, capital theta. It depends on E and the field that's generated by that primitive character, and write it as a sum of elements in the Galois group, the elements being the a sum of, with coefficients in the Galois group, the coefficients being theta coefficients. So we have that this sum of modular symbols weighted by chi is chi of the theta element. And the Birch-Stevens theorem tells us that that weighted sum is essentially given by the L function of the elliptic curve twisted by the conjugate of chi at s equals 1, the value at s equals 1 times more elementary elements. So that's what the Birch-Stevens theorem says. You go from a weighted sum to a special value. But you do it in 4 steps, or at least I want to do it in 4 steps. But I should also point out that we're interested in the end, I'll be interested in making a heuristic for a conjecture about how often an L function twisted by chi with the special value of the L function at s equals 1 can vanish. And the answer is, at least if the degree is d and chi cuts out f over q, and you have that this vanishes if and only if this weighted sum vanishes. So we're interested, whoops. Hold on.
Call from DA Consulting. Call from DA Consulting.
Oh my gosh, this is bad. Okay, so so I want to say is that the Birch-Stevens theorem connects the statistical structure of modular symbols, the theta coefficients, theta elements, and L values. Now, as I said, we're interested in making a very convincing heuristic for a sort of a conjecture about vanishing of these L values. And that was our first main mission, we thought. But we got, in some way, attracted to another aspect of that mission, and that is that, strangely, the statistical nature at each of these points in the Birch-Stevens theorem, the statistical nature of modular symbols, theta coefficients, theta elements, and L values are all different. And so we became interested in their in the specifics of their statistics, and we still are. We're still working, and I'll try to mention where we are at the moment. So start with the modular symbols. Sort of every time you have a data set, what you have to do is you have to normalize the data set to get a sort of a reasonable statistical distribution for it. And the modular symbols, they grow, well, they have an upper bound that is logarithmic in their denominator. And so dividing by the square root of the log of the denominators is the right thing to do. And you produce this multi-set SM for each M. And then you could take the collection of them for M less than X. I'll call that sigma X. And we began to make conjectures about them, and there are now really beautiful theorems by a number of people. The first being by Petridis and Rieseger. They prove that there's an explicit value in R such that as x goes to infinity, the distribution of the union of the SMs for m less than x, the sigma x's, converge to a normal distribution with mean 0 and variance, this VE. And the variance is essentially the L function of the symmetric square of E at S equals 1. And by essentially, I mean there's a small factor that is easily, it's an elementary factor. We conjecture much more is true, in fact, that the individual SMs, if you just consider them one after the other, they converge to a normal distribution with mean 0 and variance of VE. In other words, modular symbols behave in a Gaussian way. Well, if that's true, we can now ask, how likely is it that these weighted sums are 0? And I want to fix the situation. I want to fix the order D to be prime because it's easier to talk about. So we have a character chi of conductor M and prime order D. And if we pass to the theta coefficients, let us say gather together the terms weighted the same way by chi, you get this formula. So all you have to do to get sigma chi of A over M to be 0 is, well, it's rather amazing in some way. You want all the C alphas to be equal in this case. That is to say, all the C alphas corresponding to our fixed elliptic curve and the field F over Q. So what do we know or conjecture about the statistics of these theta coefficients? And I'm going to stick to the case where D is P prime. Well, first, these C alphas, there are some of a certain number of modular symbols. And after all, the modular symbols are Gaussian in their distribution. And so there's all sorts of statistical theorems like the central limit theorem and so on. And it's also true that we know not only about their Gaussian nature, but we even have a sense of what the variance is. So you might expect that as m goes to infinity, the collection of all these C alphas, these theta coefficients, appropriately normalized, given what we know or conjecture, that it satisfies a normal distribution with variance 1. But calculations, I say seem to show, they actually show this is not the case. It doesn't look too far off. And I'm going to give a few examples. For example, when P is 3, small p is really interesting. I'm taking the elliptic curve to be of the one of conductor 11 that all of us know. And I'm making a histogram of the alphas running through the cosets of index P. And we get this histogram. The red curve is the Gaussian with the expected variance. And we have this skyscraper here. If we begin to move from p equals 3 to higher p, the skyscraper gets smaller and smaller and smaller. And so you might imagine, okay, you would conjecture about these theta coefficients is that as the degree of the field to which they're attached, if you fix such a degree and consider only the C alphas of that degree, as the degree goes to infinity, you might expect that the distribution is normal, but not P by P, so to speak. So what can you imagine it will, these especially small p's, will satisfy statistically? We came up with this notion, I'll call it controlled. Controlled versus convergent, by the way. I'll talk about that in a moment. So let's consider a collection of finite sets of numerical values. And I want to index them by infinitely many positive integers, and I'll take the union of all of them as the, so to speak, height goes to infinity, all of them of height, if you wish, less than x. I'll call that d of x. And I'll say that d is controlled if there's a constant kappa such that for every real interval, the lim sup of the number of elements in our d of x in that interval divided by the number of elements in d of x itself is bounded. I'm not saying anything about what it's equal to, but it's bounded by this kappa times the length of the interval. And I'll refer to kappa as the kappa of the control bound. So our theta coefficients, when appropriately normalized, controlled. So, well, the theta coefficient is a sum of about phi of m. Phi is Euler phi function of m over d modulo symbols. And we've already mentioned that if, well, we've already seen that the A over M's are Gaussian, and if these C alphas were randomly chosen, modular symbols making up the C alphas, you would expect that the data converges to a normal distribution. We've just seen that that doesn't happen. And in addition, random matrix heuristics. Now, in the links I give appropriate references, and one of the main reference for me is the work of David, Fernley, and Kizilevsky, which was really the inspiration of everything we do. And this is, they predict that the data above, the data I've just shown you for d equals 3 won't even converge to a non-zero distribution, and d equals 2 is even worse. But our calculations support the following weaker conjecture, which is going to be more than enough for our purposes. So I want to normalize my theta coefficient, and I'm normalizing it by a beta and a gamma, that is, say, a log of the conductor to the beta minus a half, and an m to the gamma. And hope that this looks like a sort of a fairly reasonable distribution. And here's our guess. Our guess is that for every d, there are those betas and gammas such that the theta coefficients normalized by these exponents beta and gamma for the alphas that are real cyclic extensions of Q of degree D, and considering them where their conductor is less than or equal to X, that set of data as a function of X is controlled, and their kappas are uniformly bounded. And not only that, we conjecture that the gamma itself goes to 0 as D goes to infinity, and it goes to 0 in this specific way, and that the betas themselves go to 0. Now, the D equals 3 case is really interesting. The random matrix heuristics developed by David, Fernley, and Kozlowski and Kawata suggest that you can actually take your gamma 3 to be 0, that is, say there's no m to the gamma, and the beta 3 to be specifically 3/4. And our data suggests that as D gets larger and larger, you can always take gamma D equals 0, and the beta D is converting to 0 for large D. But there's also an issue of correlation, as we saw before, of correlation of theta coefficients in a given theta element. So I'm going to let D be prime, and chi a Dirichlet character of order that D that cuts out F over Q. And recall that we have that vanishing of LE chi 1 is the same as vanishing of this thing. And if the order D is P, that's equal, that's the same as saying that all of the C alphas are equal for all alpha. So that is to say, to get vanishing, you have to have lots of correlation in the theta coefficients of the same theta element. Now we introduce in our paper what one, I don't know whether we have a name for it yet, but we call it logarithmic, I don't know, if Carl is here, he might either agree or not, but I'm hoping that we will call it logarithmic correlation, and that we are going to conjecture. And in order to get some sense of the correlation, we have to consider distribution of theta EF. After all the C alphas, all the coefficients of a given theta have to be considered together. Now, if D is a prime, and if, for example, the elliptic curve has rank, positive rank over Q, there are enough symmetries in the theta coefficients so that you will need only consider D minus 1 over 2 of them. So if D is 5, you need only consider 2 of them, and so you can produce a 2-dimensional graph. Otherwise, you have to consider higher dimensional graphs or take cross sections. And so here's what it looks like as the F's run through the first 24,000 quintic extensions, cyclic Galois quintic extensions of Q with prime conductor. So we call that star-like structure. The star-like structure gets less and less star-like as we consider higher D, but we are just in the beginning of computations of that sort. So that's where we are. And as I say here, we formulate a natural conjecture. I call it natural, but I hope it's natural, conjecture about correlations that, along with the conjecture that I already sort of displayed, strongly support the guess that we had made a few years ago, but we're hoping to have more support for it on a statistical level to complement whatever support one also gets from it from random matrix heuristics. Anyway, the heuristic conjecture or the guess that we have is that if L is an abelian field extension that contains only finitely many subfields of degree less than or equal to 5, its Mordell-Weil group is finitely generated. So we'll continue to make computations. We hope those computations will corroborate our conjectures, but we'll do this certainly with fond memory of Peter Swinnerton-Dyer. Thanks.
So thank you, Barry. So now we have plenty of time for questions. I don't know quite how we decide who in what order, but maybe someone should just start by posing Barry a question.
Hi.
I have a question.
Yep.
Can I just, hi Barry, thanks for your lecture. I was wondering, so these modular symbols encode the values of L functions with the curves twisted by abelian characters. There are analogous objects for the elliptic curve based change to a real field. Where one
Say it again, say it again.
Yeah, there are analogous objects for elliptic curves based change to a real quadratic field where one considers geodesic cycles.
Yes.
On the upper half plane and so on. Have people considered those statistics, and are they similar to what you find for the?
You know, that's a good question because they people, I think, including Peter, have thought about that a tiny bit during the times when computers were not really as capable as they are right now. And I think it's absolutely worth doing. And in fact, while one is thinking about that, there is such a thing as a modular symbols for automorphic forms on GLN cross the GL1 and over also complex imaginary fields are interesting and classical, by the way. So none of that has been, as far as I know, has been subjected to modern computers. And nor do we have any real conjectures about their statistics. What fascinates me is that there has to be a much stronger conjecture about the theta coefficients than what we give. The reason why we give such a weak one is the weaker the conjecture that still gives us our heuristic, the better for us, because the more likely the heuristic is correct. That is to say, the more likely what do I want to say? The rank of the Mordell-Weil group of these large abelian fields is finite, which is what we were initially after before we got hooked into being fascinated by the statistics themselves. Anyway.
Maybe a bit of a follow-up question. I mean, do you have a sense of what your conjecture, your heuristic on finiteness of Mordell-Weil rank would be over number fields? So I guess it has to be amended a little bit because it can't always be true.
Oh, yeah. No, it definitely has to be amended. I mean, at the very least, one would want the elliptic curve to have, to be cautious, the first thing you would want is that the number field is itself generated by the J invariant of the elliptic curve you're dealing with. That, if you don't have that, you're quite lost. That's one thing. The other thing is, as you and I know, there's the Heegner points. You know, those Heegner points, you could go up an anti-cyclotomic extension and you will get infinite Mordell-Weil rank just going up this very thin skyscraper of the anti-cyclotomic extension if the Heegner points are cooperate. So you want to avoid that. In other words, you better keep away from real, characters with real values. Quadratic, the minute you have a quadratic subfield, you're pretty much in trouble in any of these conjectures, or in any of the, not only conjectures, in any of the computations that one gets. So D odd would be a first safe hedge, if you want. But I think it's I think it's just the right moment in to study the modular symbols that you get from modular symbols from GLN cross GLN minus 1 as well. These are classical things, and they come as beautiful cycles in the right space. Worth studying.
So are there other questions?
Can I ask something?
Sure.
Sure.
So do you know whether this expected distribution will tell you something about the distribution of the Tate-Shafarevich group, or is that, or do you need to make it stronger for that?
I think you better make it. That's a good question. I think we would have to have it stronger than what we have. I mean, after all, I think, yeah, the short answer to your question is no, as we have it. Slightly longer answer is I better go home and think of what strength we need in order to say anything at all about values other than special values. Yeah, and I mean the values rather than there being 0 or not, but it might be not much more.
Further questions? Sorry, but Barry, go on.
The interesting thing is when the A and B in the interval that you're considering the interval gets smaller and smaller and smaller, and it's nice to consider exactly where it gets smaller. And in any case, it will take more work. I'll get back to you. I'll email you. Yeah, your question, John, you were saying something?
So are there more questions? Well, then I think we should thank Barry very much for his beautiful lecture. And I don't quite know how we do this on Zoom. Do we clap?
Yeah.
Thank you, thank you, thank you.
And we shall, sorry? Brian, did you want to say something?
Oh.
So we shall start again with the next lecture by Henri Darmon at 15 minutes, at 3:15. 3:15 sharp with Henri's lecture. Okay?